Welcome to the very first class of electrochemistry. In this chapter, I'd like to introduce about the concept, very basic concept, and also definition of electrochemistry. So the title of chapter 1A is Overview on Electrochemistry with two thought experiments. So let me read through the content of this chapter. The first subchapter is about the definition of electrochemistry, and then let me go to the second and third. I will use two different thought experiments. In the number one thought experiment is the case of dipping an iron bar into water. So there is a beaker and also water inside there, and then I will put the iron bar, Fe bar, into the water. And then what happens on the surface, and also what happens inside of the iron bars. Based on this kind of investigations, I'd like to introduce the concept of reduction potentials. This second one is the most important part of this chapter. And then we will move to the concept of electrochemical ordinate, also electromotive force, or sometimes called EMF. Then I'll explain about the electrochemical cells. As you know, or as you expected, we have two electrodes normally in electrochemical cells. One electrode would provide some electrons, and also at the same time the other electrode would consume the electrons. Therefore, we could observe some electron flows between two electrodes. That is the electrochemical cells. The followings would include how to make the electrochemical cells working again, and also the concept of circuit and also Faraday current would be presented. The Faraday current is the current generated by reduction electrochemistry and also oxidation electrochemistry. Then the last sub-chapter is the configuration of the number one thought experiment. Then finally we would reach the second thought experiment, which is related to the corrosion of metals in contact. You should recognize that the corrosion is belonging to the electrochemistry. Okay, here we go. What is the electrochemistry? I'm saying about the definition of electrochemistry. Electrochemistry consists of two keywords. Electro, that is the first keyword, and the second one is chemistry, that is the second keyword. Electro indicates electron, of course, or sometimes current, sometimes potential. The chemistry is the chemical change. So, by using electrochemistry, you can convert the chemical energy into electric energy. Also, you can convert the electric energy into chemical energy. So it means we could define the electrochemistry in two ways. In the first definition, I'd like to define the electrochemistry as chemistry controlled by electrons. In this case, I have taken the first keyword, electro, as the driver, and the second keyword, chemistry, as the process, resultant process. So the electrochemistry can be defined as chemistry, the process, controlled by electrons, the driver. So in this case, you will apply potential or current into the electrochemical systems. Here is the example, the load of the ring. So I have the ring. Actually, this ring, originally, this ring is shaped, no. This is the ring-shaped ion. I means Fe, very cheap metals. So I'd like to coat those cheap metal by gold, very expensive metal. So how we can do it? Just to put the ion ring into the solution. The solution should contain maybe water plus some gold ions. Then apply some potential into this ion ring. Then what happens? Gold plus ions in the electrolyte would get the electron, and then finally which is converted into gold metal. Then again the gold is plated or electrodeposited on the surface of ring-shaped ion ring. Then finally we could get the gold ring instead of ion ring. This is the event or case based on the first concept or definition of electrochemistry. In this case, we have used the electrons like a driver, and then the resultant process is the chemical change from gold ion into gold metal. So this is the first definition of electrochemistry. In this process, you have changed the electric energy into chemical energy. Let's go to the second one. The second definition is electrons released by chemical reactions, or I can say electricity generated by chemical changes. The good example could come from lithium-ion batteries. Oh no, so one more things. So this second concept would be obtained by taking the second keyword as the driver. This one is driver, and the first keyword electro as the resultant process, the electricity. Okay, so let's go to the lithium-ion batteries. As you know, this guy is very important and very famous energy storage devices. What happens inside of lithium-ion batteries? Of course, lithium-ion batteries have two electrodes. Let me say the first one is the positive electrode, or sometimes cathode, but never mind about the name of cathode or anode. Just let me say the first one is positive electrode. Let me write down positive electrode, and the right electrode is negative electrodes. Then what kind of materials have we used for each electrode? The first one is lithium cobalt oxide, and the other thing is graphite. And lithium cobalt oxide would provide the lithium source into the system. So let me check the oxidation number. Oxygen atom should have the 2-, right? So this one is 4-, and lithium would have the 1+. So the oxidation number of cobalt is 3+, right? This one is 3+. Then right now you have applied potential into this material, lithium cobalt oxide, by positive potential, right? So this 3+ is going to 4+ cobalt. Then of course those electrons belonging to the cobalt is going to this way. Right now you have applied some potential into the system. So you are pumping out the electrons from cobalt oxide. Then you will use those electrons onto the other electrode. Anyway, I'll explain about that later. So right now, the 3 plus of cobalt is going to the 4 plus cobalt. Then, cobalt 4 plus would be balanced with 2 oxygens. Then, this lithium plus ions would not have found their position inside of the crystal structure of lithium cobalt oxide. So, lithium plus ions is right now going out from the lithium cobalt oxide. Okay. Then this electrons is going to the other side of electrode. Here you have found right now the graphite. So graphite consists of multiple layers of graphene, and right now these graphene layers have some extra electrons, right? So, and also you have an extra amount of lithium plus, which is going away from the lithium cobalt oxide. So, due to the electrostatic force, lithium plus is going to the graphite, and then finally this is placed between the graphene layers of graphite. So finally graphite is, let me say graphite is C6, it's going to lithiated graphite. Then this is the charging process. What did you do? You have applied potential like positive on the lithium cobalt oxide and negative on the graphite. Then finally you have made just cobalt oxide and also lithiated graphite. That is the charging process. And the charging process of lithium-ion batteries is belonging to the very first definition of this one. You have used the electricity to charge the batteries, so controlled by electrons, and lithium cobalt oxide is converted to cobalt oxide. At the same time, C6 graphite is going to lithiated graphite. Chemical changes. So charging process is based on the very first definition of electrochemistry. Then it's time to introduce the second definition example. So right now you have a charged lithium-ion batteries, and then you will connect those two electrodes into some cell phone and or sometimes laptop or electric vehicles or anything. Right now you have high energy lithiated graphite. Also you have a high energy cobalt oxide. Instead of just graphite, instead of just lithium cobalt oxide, those two guys are very energetic ones. And also lithiated graphite want to be converted to be original graphite, or cobalt oxide want to go to lithium cobalt oxide. So when those two electrodes are connected to some resistance or load or laptop or your cell phones, then electron flows from here to here back to there. So finally lithium C6 is going back to C6, and also cobalt oxide is going back to lithiated cobalt oxide, lithium cobalt oxide. So then you could get some electricity by using chemical change of this one and this one. So this is the example of the second definition of electrochemistry. Again, the second definition of electrochemistry is electrons released by chemical reactions or electricity generated by chemical changes. So those are two different. You have just learned the definition of electrochemistry. Then it's time to go to some experiments. Here I have one very simple experiment. Iron bar, and here is water in the beaker. I have just put an iron bar into water in the beakers. Then let me guess what happens on the surface of iron bar, and also what happens inside of the iron bar with water in the beaker. Let me magnify the surface atom from here to there, and then maybe it would be a neutral atom. Of course, one single neutral atom consists of nucleus, positively charged one, and the electron clouds, which is the negatively charged one. The positive charges are balanced with negative charges in the neutral atom. So we can say this atom is neutral in terms of the charge balance. But at a certain circumstance, some portion of electrons belonging to the electron cloud is going away from atom side into its surroundings. In this case, 2 electrons is going away from atoms. Then finally, you could find some positive ions. Maybe oxidation number is in this case 2+. This process from neutral atom into positive ion is called ionization or ionization. Specifically, in these positive ion cases, this process can also said to be oxidation, because the oxidation number increases from 0 to some values of positive charges. Again, here is the ionization processes, and this ionization process have some splitting of neutral atom into positive ion and electrons. Each atom, each molecule, and each material has its own ionization strength or ionization tendency. Here are 6 atoms: sodium, zinc, iron, copper, gold, platinum. Sodium atoms ionize dangerously easily. As you know, sodium belongs to the first column of periodic table or alkaline metals. The atoms belonging to alkaline metals would have just 1 electron in the outermost shell of electron cloud. So sodium or the other guys like the lithium or something like that would lose its own 1 electron in the outermost orbit into outside very easily. So we could expect sodium atoms ionize dangerously easily, of course. Again, lithium metal belongs to this kind of category. So lithium atoms also ionize dangerously easily. It is the reason why we have used the lithium metal in the lithium-ion batteries. Of course, we could use the sodium atoms for making new batteries. Let's go to the second one, zinc. Zinc atoms ionize easily. It means zinc could be used as some materials for batteries. Zinc atoms ionize less easily than sodium, but zinc atoms ionize very easily when compared with other atoms or molecules. The third one is iron. Iron atoms ionize fairly easily, less easily than zinc, but fairly easily. We are thinking about the iron bar here. In daily life, we have often met some rust, which is the red iron oxide. The rust is the material obtained by oxidizing the iron, because iron atom ionize fairly easily. The next one is copper. Copper atoms ionize with some difficulty. Sometimes we could find copper oxide, but also we could find copper metal on Earth. The gold atoms ionize with great difficulty, so it is very difficult to find gold oxide. How about platinum? Platinum atoms ionize hardly at all, so it is almost impossible to find the platinum oxide. Of course, very thin film of platinum oxide is found on the surface of platinum metal. So from a very ancient time, platinum and gold have been considered as a kind of jewelry. Why? Because they are shiny. Why are they shiny? Because they are existing as metals instead of metal oxide. Look at the stone. What is the stone? Stone usually consists of silicon oxide and aluminum oxide. It's very difficult to find just silicon metal or just aluminum metal, because they are very easily oxidized or they easily ionized into its oxide form. So we cannot say it as a jewelry or shiny thing. However, it's very difficult to ionize or oxidize gold and platinum into its oxide form. So we can easily find its metal form on Earth. So gold and platinum are shiny, and of course we call them as jewelry, shiny jewelry. Okay, I have said about 6 different elements or metals in this case, and there's some oxidation easiness trend or ionization easiness trend. Along the direction from platinum to sodium, oxidation easiness or ionization easiness increases from here to there. That is to say, sodium is easily oxidized, while platinum is difficult to be oxidized. You know, reduction is the backward process of oxidation. So of course, the trend or the tendency of reduction would be contrary to the direction of oxidation easiness. So the direction from sodium, along the direction from sodium to platinum, the reduction easiness or reduction tendency is stronger and stronger and stronger. So finally, platinum is always reduced. However, it is very difficult to reduce sodium atoms. We learn about the reduction potential, and the values of reduction potential would follow the direction of reduction easiness. Therefore, the reduction potential of platinum is the most positive value, or the highest value. On the other hand, sodium would have its reduction potential at the lowest value, or the most negative values. So the reduction potential would follow the reduction easiness. Let me get back to the experiment. Here, still, we have an iron bar in the water. Then, in the previous slide, I have tried to depict some surface atoms of an iron bar as some circles. And then I have explained about the structure of each atoms. And also, I have said each atom has its own ionization strength, or reduction strength, or oxidation strength. So let me apply this kind of things into these pictures from here to there. So right now, look at the surface of an iron bar. We have several positively charged species on the surface of that iron bar because of the ionization strength of iron atoms. Let me say we have 20 ionized surface species on the surface of iron bar. And what happens, or where can we find the electrons originally belonging to those 20 ionized surface species? Can you find those electrons in the electrolyte or water, or inside of the iron bar? Of course, the second thing is the answer, iron bar. I mean inside of the iron bar. Water is not the electron conductor, so the electrons coming from those surface species is not going to the water. Instead of water, those electrons would find some way into the body of an iron bar. So you can find in this picture some dots inside of the iron bar. That is the electron. So let me say we have 20 ionized surface species which is positively charged, and also 20 extra electrons are found inside of the iron bar. So charges are balanced to each other. From the viewpoint of the positive surface species, from here to there, we have two attractive forces. One from the electrolyte side or water side, the other from the metal side or electrode side. Let me focus on the water molecules here and here. Then we have an oxygen and also two hydrogen atoms. Water molecule is a polar molecules and it has some dipole. Of course, negative charge on oxygen atom and positive charge on hydrogen atom. When those water molecules meet some positively charged surfaces of some metals, then the direction of dipoles are oriented and also aligned toward the charged surfaces. In this case, negatively charged oxygen atom is going toward the positively charged metal atom on the surface. So something like that. So of course there is some attractive forces between plus charge on the surface and negative charge on the dipole. That is the first attractive force. And let's go to the second one, coming from the metal side. Of course, I have said we have extra electrons inside of iron bar which originates from actually the surface species. Those electrons would exert an attractive force onto the surface species which is positively charged. So there are two attractive forces in this picture. If those are well balanced, nothing happens. Or if the second attractive force is stronger than the first attractive force, nothing happens. I mean, those positively charged species are still there on the surface. However, if the second one is stronger than the if the first one is stronger than the second one, of course, those ionized species is dissolved from the surface into water, something like that. So some portion of matter or ion is dissolved in water. Again, ion here, and ion case have 20 positively charged surface species with 20 extra electrons in the metal body. Let me extend this ion case into other metals like sodium, copper, and gold. As you know, sodium is really easily oxidized and ionized in an extreme way. So we would have a lot of ionized species on the surface actually dissolved into water. So let me say we have 100 positively charged surface species plus 100 extra electrons in the body of sodium metal. So I have said 100 plus with 100 minus inside of the body of sodium. So 100. Let's go back to the other side. Gold case. It is very difficult to oxidize gold, and in this schematic picture I have drawn only two positively charged or ionized surface species. So two ionized surfaces with two extra electrons in the gold body. So let me say two. The last one is copper. Let me say 10 ionized surface species with 10 extra electrons. So right now we have a kind of series of metals like that, and then in the body of matter 2 electrons are found in the gold, then 10 electrons are found in the copper, then 20 electrons are found in the iron bar, and finally 100 extra electrons found in the sodium metal. So let me count the number of extra electrons in the body, and the reduction potential would follow this number of extra electrons. Again, let me say 2 electrons. It means 2 minus, maybe, schematically, and 10 minus for copper, 20 minus iron bar, and 100 minus sodium metals. So it means the reduction potential of gold bar is the most positive one, minus 2, most positive one. The next one is copper, minus 20. Minus 10. It means the reduction potential of copper is more negative than the reduction potential of gold. How about iron bar? Minus 20. More negative than copper and gold. How about sodium? Minus 100 electrons. So the most negative reduction potential would be obtained from the sodium metal. So that is the reduction potential. Of course, actually the reduction potential of gold is not minus 2, some value. But anyway, the right thing or the truth is that the gold would show the most positive values of reduction potential. Again, reduction potential is related to the charges of extra electrons. Then plus values would favor reduction, and minus values of reduction potential favors oxidation. Why? You know, the sodium is really rich guy in terms of electrons. 100 electrons the sodium matter have. So this guy could donate their own electrons into the other guys. It means sodium would be easily oxidized into sodium plus ions because this guy is rich in terms of electrons. However, let's get back to the other extreme case, gold. Gold is the poorest guy in this series. Just 2 electrons the gold metal have. So this guy wanna get some electrons from other guys, accept some electrons. It means gold is easily reduced, not oxidized. So the plus values of reduction potential would favor reduction, and minus value indicating a lot of electrons are there. Anyway, minus value of reduction potential would favor the oxidation. I have just copied this picture from the previous slide into this slide. Again, gold in the water and copper in water, ion, and then the sodium. So I have said gold has 2 minus extra electrons inside of the body, 10 minus for copper, 20 minus for ion, and 100 minus for sodium. So I'd like to map those orders onto y-axis or ordinate. Here is the ordinate, vertical arrows or vertical lines, and then gold is going to this point, and copper here, iron here, and then the sodium is there. So we have 4 elements on the ordinate. What does it mean? The positive reduction potential is located on the lower placement of this electrochemical ordinate. Also, minus side is going up. So sodium would have the most negative reduction potential, then iron, then copper, then gold. I mean, gold is the lowest, or the most positive reduction potential of this series. Why negative signs are located on the upper placement, while the most positive values are located on the lowest placement of this electrochemical ordinate. In the electrochemistry, we electrochemists are focusing on electrons, and also more number of electrons indicates in this schematic diagram, more number of electrons indicates more energetic. Only more energetic guys would donate their own electrons to poorer guys having more positive reduction potential. Anyway, so is the reason why I have just placed the more negative values on the upper side. So sodium is the most energetic in this series, so its reduction potential is most negative. Then iron, then copper, then gold, and gold is the most positive guys and also poorest guy in terms of electrons. After we have placed those guys in this direction or in this order, then we could easily expect the electron flows from one guy to the other guy. Before explaining about the electron transfer, I'd like to define the reduction potential again. I have said sodium metal have some reduction potential which would be most negative values in this series, but actually it's not true. The reduction potential is defined not on element or material, but on reactions. So I have written down, instead of just sodium or sodium plus, I have written down sodium plus and sodium. This is the electrochemical pair of species. I mean, the reduction potential is defined on a pair of electrochemical species, in this case sodium and sodium plus. Also, this pair of electrochemical species indicates a reaction. Let me change the laser point to pen, and then sodium plus sodium means sodium plus electron is going to sodium. Well, let me say sodium 0. So electron pair indicates the electrochemical reaction related to those pairs. So again, reduction potential is defined on a pair of electrochemical species like sodium plus sodium, or related reduction process like sodium plus is getting electron into sodium 0. Let me go to the other example. Here is the copper 2 plus copper. We have some values of reduction potential. This pair indicates copper 2 plus 2 electron is going to copper, or sometimes 0, something like that. So again, reduction potential is defined on an electrochemical process. Again, the reduction potential is not the characteristics of some material, but the characteristics of some process. Sometimes reduction, sometimes oxidation, anything is okay, but usually we are thinking about the reduction like that. Okay, let's go back to electrochemical ordinate. Again, here we have an electrochemical ordinate, and right now we have 4 species are placed on the electrochemical ordinate. Each pair of electrochemical species have its own some reduction potential value. Even if I said this is 2 minus, this is the 10 minus, this is 20 minus, this is 100 minus, but those values are just for explanation. Each element, well, each pair of electrochemical species has its own values. I'll let you know the exact value later. But anyway, the order of this species is following those reduction potential. Okay. Then it's time to say about the direction of electron transfer. So right now I have 2 species like that, 2 pairs of species like that. And then what happens? I mean, if you have those things in some electrolyte and then the other things in the same electrolyte, what happens? Electrons is transferred from the upper position to the lower position, always. I have said the more negative reduction potential indicates the rich guy in terms of electrons. That guy would donate their own electron into the other guys. So electron is transferred from here to there. Let me draw the picture about this same situation. Beaker, and right now you have Fe here, Fe metal bar, and then gold plus. Here's some water or some electrolyte, and then some portion of Fe is going to Fe2 plus ions into electrolyte. But at the same time, gold plus is plated or deposited on the surface of ion bar. This is the gold medal, and also you can find Fe2 plus in the electrolyte. That is the situation. So after electron transfer, what happens? Fe is going to Fe2 plus by donating its 2 electron into gold 2 plus. At the same time, gold 2 plus would get the electron from ion into gold 0. Those reactions are going in these situations. One is reduction, right? The other thing is oxidation. Reduction is always paired with oxidation. Oxidation is always paired with reduction. Then the charge transfer balance is 0. Okay, one more things. From those two pairs, we have expected these guys. But I can suggest another situation with the same pairs. Right now, you have gold. And in the electrolyte, you have Fe2 plus. What happens? One of my students would say, okay, I can read some values of reduction potential on the electrochemical ordinate. According to the electrochemical ordinate, Fe species donate their own electron into gold species. So Fe2 plus donate each electron to gold, and then gold is reduced. Is it right? I don't think so. Fe species would experience the reduction, right? Fe is going to Fe2 plus. So Fe is reduced species, and Fe2 plus is oxidized species. However, Fe2 plus, which is the oxidized species, cannot donate the electron into the other pair. So there are no electron transfer from Fe2 plus. At the same time, if you have a gold 2 plus, maybe this gold 2 plus would get some electrons from outside. However, you have already had gold 0. So gold 0 cannot get the electrons from outside. So nothing happens in this situation. Again back, you should have only Fe and gold plus, then you could observe the electron transfer. However, if you have another of the electrochemical species like gold and Fe2 plus, you cannot get any electron transfer. So you should have reduced species for making the oxidation. You should have oxidized species to get some electrons from other side. So, you should understand those two different cases. Okay, let me summarize this slide. Let me read some text. Species of more negative potential are rich of electrons around there. It is ready to donate electrons to other species of more positive potential. So, for example, Fe species is donating their own electron into gold species. The species are oxidized after donating electrons. Of course, Fe is going to Fe2 plus. That is to say, more negative potential indicates oxidation is favored. Okay, that's it for the electrochemical ordinate. There is a small correction of my explanation. Let me change to pen. So I have said about the electron transfer from here to there, and Fe is going to Fe2 plus. At the same time, gold plus is going to gold. Then in my previous explanation I have said this is the reduction, but this is the reduction, but it's wrong. This is the oxidation. And at the same time we would have the reduction here. So oxidation is matched with reduction, and reduction is matched with oxidation. That is the correction on my previous explanation. Let me discuss about the electromotive force, shortly EMF. What is the EMF? You have just learned about the electron flows or electron transfer from one material to the other material. One makes this kind of flows of electrons. So let me get back to the electrochemical ordinate here. There is a tiny difference between this electrochemical ordinate and the same thing in the previous slide. What is that? That is here is the exact value of reduction potential presented. So we have the same methods given to you in the previous slide, like gold plus is going to gold, copper 2 plus is going to copper, Fe2 plus is going to Fe, sodium plus is reduced into sodium metal. So we have 4 electrochemical pairs of species. And each electrochemical pair or electrochemical each pair of electrochemical species have its own reduction potential. So let me check it. 1.68 volt or plus 1.68 volt for gold plus gold. So you can feel that. Okay, this guy would be well reduced because it has the very positive reduction potential. It means there are no the extra electrons, or very small amount of extra electrons in each body. So there are no money. That is to say, the gold would not donate their own electron to the other guys. Anyway, plus 1.68 volt. Then you can think this guy is very poor in terms of electron. Then the other thing is 0.34 volt for copper, minus 0.41 volt Fe2 plus to Fe, and minus 2.71 volt is going to sodium plus sodium. So we have 4 species on the electrochemical ordinate. And if you have 2 metals like Fe and copper, maybe you could expect the voltage difference between them. 0.34 volt minus 0.41 volt. So the resultant gap is 0.75 volt, something like that. That is the electromotive force. This motive force makes electrons flow from Fe to the copper part. Okay, let me have some more realistic situations. Actually, this is the schematic situations. We have a beaker, water, and 2 metals. One is copper and the other is iron, Fe. Then just after you put those metal bars into water, something changes on the surface and something changes is followed in the body of metals. Copper, I have said, schematically, I have said 10 surface species are ionized. So you could find 10 extra electrons in the body of copper. So you could feel some electron pressure, the amount of which is equivalent to 10 extra electrons. The same thing here for the ion bar. 20 surface atoms or species is ionized, so you could easily find 20 extra electrons in the body of ion bar. So you would feel some electron pressure exerted by 20 electrons. So I'll try to measure the difference between those electron pressures. That is the electromotive force. So I'd like to use voltmeter. This device would measure some voltage difference. So right now, the positive pole of voltmeter is connected to the copper, and then minus pole is connected to ion bar. So voltmeter will read the voltage gap or reduction potential gap between copper and ion bar. More detailedly, maybe this device will read the potential of copper, because which is connected to positive one, with respect to the reduction potential of ion bar. So minus sign indicates some reference. So this value minus this value is going to the potential gap or reduction potential gap, which is displayed on this voltmeter. Let me change my pointer to pen here. So copper, what is the reduction potential here? So plus 0.34 volt. And how about the reduction potential of ion bar here? Minus 0.4 volt for 1 volt. So the values displayed on voltmeter would be estimated by subtract the positive one minus negative value. So minus. Then finally, I can say the displayed value should be plus 0.75 volt. This electromotive force will make some electrons flow, but not now yet. Not now. Because voltmeter have a lot of big, not a lot of, the voltmeter have a big resistance inside. So there are no electrons, or this way or that way. It's not allowed. Of course, very small current would flow, but usually no current there. So we have measured the reduction potential between those two things. That is the voltmeter. And this is the electromotive force. This potential gap could be denoted by rest potential sometimes, and also open circuit potential. So this is the electromotive force, and the potential led by voltmeter in this situation is called rest potential or open circuit potential. Rest potential is the potential difference between two electrodes without any disturbance. So it is called rest potential because there are no any disturbance. And sometimes it is called open circuit potential because there are no electrons flow through the circuit. This rest potential or open circuit potential is the happiness state at each open circuit. Okay, that is the electromotive force. We are still on this cell containing copper and iron bar in water. So it's time to connect those two electrodes by metal wire. Then maybe electrons would find some super high pathway for conduction. Then electron flows from some one electrode into the other electrode. We have already known the direction of electron flows from the lesson of electrochemical ordinate. Let's go back to the electrochemical ordinate. The reduction potential of Fe2 plus Fe pair is minus 0.41 volt. The reduction potential of copper 2 plus copper is plus 0.34 volt. That is to say, the iron thing have more negative reduction potential than copper things. So, electron is donated from Fe to copper 2 plus. At the same time, Fe is converted to Fe2 plus, and also copper 2 plus is going to copper. So we have already know this kind of flows. So what we know is the direction. But my question is, how many electrons flow from iron to copper? Let me check the numbers in these schematic pictures. Again, I have said iron have 20 electrons in the body. That is to say, we have 10 Fe2 plus ions on the surface. Also, copper have 10 electrons, which is equivalent to 5 copper 2 plus ions on the surface. We would feel some electron pressure from iron bar and also copper bar. In this case, the electron pressure exerted by iron bar would be around 20 electrons. Also, copper would have the electron pressure which is equivalent to 10 electron. That is to say, the electron pressure of iron bar is higher than the copper bar. So electron flows from iron to copper as expected from the electrochemical ordinate. So let me move some electrons from iron to copper. So here's 2 electrons, and I want to get these electrons from iron bar into copper. So let's go to the second picture. Then electrons is disappearing in the iron bar and then moving to the copper. And then the copper 2 plus species on the surface of the copper bar is reduced into copper. So let me read some text. In the copper side, electrons coming from Fe attract copper 2 plus surface species more strongly. Then ionization is hindered or reversed. So copper 2 plus on the surface, this one, is getting 2 electrons, then finally go to copper 0. Okay, that is the first step. And also, let me get 2 more electrons here, then move to the other 2 plus. So we have another reduction process here. So copper 0. One more thing, copper 0, copper 0, copper 0. So the whole reaction proceeds until the surface ionized species are totally neutralized. So let me get back to the original question. How many electrons would flow in this cell? The answer is 10 electrons because we have 5 ionized surface atoms of copper 2 plus. So 10 electrons are required to reduce the 5 copper 2 plus ions on the surface. Then the amount of electron flows is 10 electrons. Let me check what happens on the Fe side. Due to the electrons flow away to copper side, then the attractive force to hold Fe2 plus on the surface becomes weaker. Then Fe2 plus surface species is dissolved in the electrolyte. So this Fe2 plus is going away from the surface into electrolyte. Of course, next one, this one, the other one, this one, this one, this one. 5 Fe2 plus is going away from the surface and finally dissolved in electrolyte. Of course, also this kind of 5 Fe2 plus ions indicate 10 electron flows. Moreover, fresh surface atoms may be around here, 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 here. Fresh surface atoms are exposed to electrolyte, of course, because Fe2 plus is going away from the surface. Then more surface atoms are ionized. Sorry. However, the ionization stopped when the process in the copper side did. So the transferred electrons would be just 10 electrons. After this process, we don't have any more electron transport or flows along the matter wire because we don't have any more copper 2 plus ions. I want to feed some babies, but there are no babies on the copper side, so there are no more ionization in the ion side. After 10 electron movement, we cannot have any more current from the cell including copper and ion bars. So current is 0. Every surface species of copper is totally reduced into copper 0. 1, 2, 3, 4, 5. Then there are no babies on the copper side who should be fed by the electrons from ion bars. So no more current. Here's the question. How can we make the electrochemical cell work again? Or how can we generate the electricity from this cell? There are various methods would be exist for survive or regenerate these electrochemical cells. Let me get back to the electrochemical ordinate. We have Fe pair and kappa pair, right? And at these cells, at the very first time, Fe donated their own electron into kappa 2 plus, then Fe is going to Fe2 plus, and kappa 2 plus is going to copper. But right now, the problem is that there is no kappa 2 plus. No more babies there. So the solution is like that. Any species, actually any oxidized species is introduced into the system, which should have the more positive potential, more positive reduction potential than Fe2 plus Fe. Then this cell is working. Here is one example. Right now we don't have any copper 2 plus. So let me introduce copper SO4. This salt is dissociated into copper 2 plus and sulfate ions in electrolyte. Then this copper 2 plus in electrolyte would try to get some electrons, and that electrons would be donated by ion bar. So in that case, copper 2 plus is electrodeposited on the copper side, getting the electrons from ion bar. Also, another copper 2 plus would be plated on the surface of Fe to copper 0. Anything is okay. That is the first solution to regenerate these electrochemical cells. Then the second method. Let me use another species different from copper 2 plus. Here, I want to use acid. For example, hydrochloric acid. Like the copper sulfate salt, hydrochloric acid is dissociated into proton and chloride minus ions. So we have a lot of protons right now in the electrolyte. And let me check the reduction potential of H plus here. The pair of electroactive species like proton and hydrogen gas has the reduction potential at 0 volt, which is more positive than the reduction potential of Fe2 plus Fe. Then also the good thing is H plus is not the reduced species, but the oxidized species. So, like in the case of copper 2 plus, Fe would donate their own electrons into proton, and then at the same time Fe is going to Fe2 plus and proton is going to hydrogen gas. So hydrogen evolution reaction happens. There are two ways of making hydrogen in this case. Of course, H plus will get some electrons on the copper side. Actually, as you know, copper, iron, and also metal wire are all conductors. So electrons are moving freely around here and there. So protons feel the reduction potential of ion bar. Then H plus is going to H2 on the copper side. One more thing. Also, there would be a direct electron transfer from ion to proton. So proton is also here, and then get the electron from ion bar directly to hydrogen evolution. However, I prefer the copper side for hydrogen evolution because, on the surface of ion bar, a lot of Fe2 plus ions. So there would be some electrostatic force, electrostatic repulsive forces between proton and Fe2 plus. So more probably the hydrogen evolution happens on the copper side. So we could regenerate these electrochemical cells by adding any oxidized species which have the more positive reduction potential than the pair Fe2 plus and Fe. So the first example was copper 2 plus in electrolyte. Also, the second example was proton into electrolyte. Let me check some text. Proton accept electrons from copper, and the electron from Fe is used to convert proton to hydrogen gas. Here is the full cell reaction. Fe to Fe2 plus to electron. Electron is generated. And by using these electrons, proton is converted to hydrogen on the ion side, but more probably on the copper side. So full cell reaction is like that. Fe plus 2 protons is going to Fe2 plus hydrogen evolution. Until now, we have used an electrochemical cell having Fe and also copper in water in a single beakers. I'd like to modify that Fe copper cells into zinc copper cells. Here is more realistic situation for batteries. This is not the rechargeable batteries like lithium-ion batteries. This is the primary cell of batteries. So right now I have two beakers. In the left beaker I have zinc. Also zinc 2 plus and nitrate anions in electrolyte. Let's go to the second beaker. On the right beaker I have copper and also copper 2 plus and nitrate anions in electrolyte. Those two beakers are connected to each other by using the salt bridge. Inside of a salt bridge you could find some gels, and the gel is saturated by sodium chloride. Of course, sodium chloride in water is dissociated into sodium plus and chloride minus ions. Okay, that is the primary cells of zinc copper cells. Let me get back to the previous example of Fe copper cells. At that time, we have used this one and this one. So the potential gap or electromotive force was plus 0.34 volt minus 0.4 volt, equivalent to 0.75 volt. But I have replaced the Fe2 plus Fe into zinc 2 plus zinc, actually zinc. Then the potential gap or electromotive force of zinc copper cells read by voltmeter would be plus 0.34 volt minus 0.76 volt is going to 1.10 volt. Then let me connect this battery into some device which should work at 1.10 volt. Then you could observe some electron flows. What happens there? As you expected, zinc is converted into zinc 2 plus because zinc 2 plus zinc species have the more negative reduction potential than copper 2 plus copper. So zinc is trying to donate their own electron into copper 2 plus. So electrons is generated from zinc anode. Then at the same time, zinc is dissolved into zinc 2 plus. Electrons going through the metal wire and then finally reach the copper electrode. And then the copper 2 plus ions in electrolyte is reduced into copper draw, then which is electrodeposited onto the copper electrode. So let me check the charge balance. on the left side beaker, maybe the electrolyte is positively charged because extra zinc 2 plus is generated from zinc electrode. So zinc 2 plus is trying to escape the positively charged electrolyte, so into the salt bridge. At the same time, copper 2 plus is consumed on the copper electrode. So the second beaker, I mean the electrolyte in the second beaker, is negatively charged. So nitrate ions is trying to escape from the right side beaker, so entering into salt bridge. At the same time, chloride minus ions is moving toward the first beaker to meet zinc 2 plus to keep the charge balance. Also, sodium plus ions in salt bridge is going to the second beaker or right side beaker to meet nitrate anions. Right now, all charge balances are satisfied. Okay, so after some time later, you could find zinc anode is sacrificed. Also, additional copper mass is electro-deposited onto the copper electrode. Please check the link of YouTube, and then you can get the more detailed explanation about the zinc copper cells. I'd like to introduce two keywords related to electrochemical cells. The first one is circuit, and the second one is Faraday current. Let's start with the circuit. The dictionary meaning of the circuit is a complete course, journey, or route round something. And also, some guys are moving along this circuit. So let me get back to the first example of the electrochemical cell. Still we have copper, iron as electrodes. And I have used the metal wire to connect those two electrodes. And then also in electrolyte, I have protons because I have used acid solution. So in this case, iron is oxidized, so Fe2 plus is generated, and also extra electrons are generated. These electrons are moving through the metal wire and then finally reach the other electrode, in this case copper electrode. Unfortunately, we don't have any copper 2 plus on the surface and in electrolyte, so there are no reduction of copper 2 plus into copper 0. Instead of it, we have the protons, a lot of protons in electrolytes. So those protons are getting the electrons, then is reduced into hydrogen gases. Then you can observe some hydrogen gases are evolved from these cells. So you can find a circuit here. Something is moving through this circle. So this circle or circuit consists of two parts or two pathways. The first pathway is found in the electrode side. Electrode side indicates two electrodes and the metal wire. Those are the electrode sides. This is the electric pathway. And the second one is found in electrolyte side. Right now, Fe2 plus is generated and moving to the copper. Also, a lot of proton are there, and then proton is moving to the copper electrode. So this is called ionic pathway, which is found in electrolyte. So let me try to find differences between electric pathway and ionic pathway. The electric pathway found in electrode size is like that. So charge carrier of this one is electron. Of course, the material of the electric pathway should be electric conductor because charge carrier is electron. Let me go to electrolyte side. Of course, this is the ionic pathways. So the charge carrier of ionic pathways are ions, not electrons. So it should be ionic conductor. So the circuit is divided into two pathways. The first pathway is electric pathway and the other thing is ionic pathways. Let's go to the second keyword, which is the Faraday current. Faraday current is defined as the current caused by oxidation or reduction. Actually, in this cell, you can find easily those kind of current here because the electron was originally generated by oxidation of ion matter into Fe2 plus, and then these electrons are consumed by reduction of proton into hydrogen gas. So in this electrochemical cell you can find a Faraday current. The name of Faraday current is after the English scientist Michael Faraday. Okay, so let me discuss about the configuration of electrochemical cells. Usually you have met two terminal configuration for electrochemical cells. These two terminal configuration is very primitive and basic configuration of electrochemical cells. Therefore, all electrochemical devices like batteries here and fuel cells have two poles or two electrodes, including positive electrode and negative electrode. Here is another example which have been used for previous slides. Copper ion cell, or actually proton ion cells, have only two electrodes, not just a single electrode, not with three electrodes or more. The potential difference between positive and negative electrodes, so-called cell potentials, can be measured. I'd like to emphasize one word in this sentence, the difference. So again, let me read it again. The potential difference between positive and negative electrodes can be measured. Why have I emphasized the difference? Because we cannot measure the potential of each electrode for this one or this one. It is allowed to read only the relative potentials of one electrode with respect to the other electrode. It is impossible to measure the potential of each electrode. So it is the reason why we electrochemists have often used three electrode system. However, I'll discuss about the three terminal configuration later. Right now, I'd like to focus on the two terminal configuration. So let me discuss about why the difference and what is the meaning of it is impossible to measure the potential of each electrode. So here is the lithium-ion batteries, and then let me change my pointer to pen. So let me assume some situations. The cathode have some potential, like let me say 4 volt, and then anode is 0 volt. So if you are trying to measure the potential between them, then the cell potential is going to forward, like forward, right? However, with some circumstances, this anode or negative electrode is going to 1 volt. Then you will need 3 volt as the cell potential. So what you can read from your cell in this configuration is 4 volt and 3 volt. You don't have any idea about the potential of each electrode. That is to say, there are no change of the positive, no change of the reduction potential of cathode or positive materials. Only changing thing was on the negative electrode. However, from these values, you cannot expect anything. No change on cathode, only change on anode, but from this potential difference, you cannot expect anything, while no idea on the potential of each electrode. The electrochemical cell have two different electrochemical processes. Actually, at least two different electrochemical processes. One is the reduction, and then you could provide some electrons into the system by the reduction. No. One is oxidation, and by using the oxidation, you can provide some electrons into the system. Also, the other thing is reduction. Those generated electrons are consumed by reduction. So, as an example, you have learned about ion reduction here, then ion oxidation is here, and then proton reduction is here. So you can make some electron transport through the conductive material in the electrode side. At the same time, some ions moves from here to there or something like that. Until now, you have learned about the thermodynamics, that is to say, reduction potentials. By using the lessons of thermodynamics, you can expect the direction of electron flows. In this case, from here to there. Also, you can estimate the values of cell potential, which is the difference of reduction potential between ion bar and the proton hydrogen pair. But you don't have any idea about the rate or speed or kinetics. How many electrons are generated by the ion oxidation for a second? Or how many electrons are consumed by proton reduction for a second or for an hour, something like that. We cannot expect anything from thermodynamics based on reduction potential. But the kinetics or the rate is a very important thing. Then we should consider those speed of the electron generation or electron consumption rate. So here is my questions. Maybe you have already accustomed to these electrochemical cells. So which process is faster than the other process? That is my question. We have two processes again, ion oxidation or proton reduction. Which one is faster than the other? So here is some hypothetical values for calculation of the rate. Here is just assumption. So let me say like that. For the Fe oxidation, let me assume that one single Fe atom would lose 2 electrons for a second. It is a kind of unit rate. 2 electrons is generated from a single Fe for 1 second. Also, I have an ion bar, and only the surface atoms is exposed to electrolyte. So let me think about the surface atoms. So my assumption is that only one Fe atom per every centimeter square on the surface of ion bar. Of course, this is not true, but this is just assumption. And also, I have used an ion bar having 10 centimeter square surface area. So then we can calculate the overall rate of the Fe oxidation. So 2 electron per second Fe. Let me change my laser pointer to pen. 2 electron second Fe and 1 Fe atom per centimeter square, and I have 10 centimeter square the surface area of electrode. Then finally we have this unit, electron per second, and then 20. So every single second you can generate 20 electrons from this electrode. Then let's go to the other electrode. On the copper electrode, the proton is reduced. There are no copper 2 plus, so there are no reduction of copper 2 plus here. So we should think about proton reduction. So proton reduction here. And then also I'd like to assume that one proton would consume 1 electron for a second. Also, every centimeter square you can find 1 proton on the surface of copper electrode. And also I have used 1 centimeter square copper electrode here. Then the overall rate of proton reduction is 1 by 1 by 1 is equal to 1 electron per second. It means 1 electron is consumed on the copper electrode for a second. So let me compare the values between proton reduction and Fe oxidation. 1 and 20. So the rate of Fe oxidation is much faster than the rate of proton reduction. Okay. So I can say the proton reduction, I can say proton reduction is rate determining step. Okay, so let me change to laser pointer. So again, on the copper electrode, only 1 electron is consumed for a second. However, ion could be oxidized at 20 electrons per second. However, we cannot use this kind of fast rate because the capability of the proton is just 1 electron per second. Your baby can get just 1 cup of milk, but you want to provide your baby like 1 liter of milk, but your baby cannot get 1 liter of milk. Just a cup of milk is the maximum value. So the overall rate of this electrochemical cell is not the 20 electron per second, not the average of 1 electron per second and 20 electron per second, but the correct answer is that the overall rate is 1 electron per second. So I mean the slowest rate would determine the overall rate. So you cannot use 20 electron per second. Okay. But unfortunately, I want to measure the kinetics of ion oxidation instead of proton reduction. But the overall kinetics is just following the rate of proton reduction. So you cannot study the kinetics of ion oxidation. How can we solve this problem? How can we estimate the kinetics of ion oxidation? How can you make the ion oxidation as the rate determining step? Here is the very simple solution. So still I have used the same ion bar, 10 centimeters square, but in this case I have increased the surface area of copper electrode. Then maybe more number of protons could be reduced into hydrogen gases. So the overall rate is 1 by 1 by 1 by 1 by 1 by 100 is going to 100 electron consumed per second. So right now the rate of Fe oxidation at 20 electron per second is slower than or smaller than the rate of proton reduction at 100 electron per second. So the overall rate is determined by Fe oxidation, the value of which is 20 electron per second. So right now, after you have increased the surface area of copper electrode, you could estimate or you could measure the kinetics of ion oxidation. It's very important concept. As a summary, rate determining process limits current. And in these electrochemical cells, we have two different reactions. Fe is going to Fe2 plus oxidation, proton is going to hydrogen gas reduction. Then, in a circuit, the current for oxidation should be equal to the current for reduction. It is so-called steady state. This steady state situation is like the situation in your student restaurant. You are in line for getting food from the restaurant, but the guy just before you are moving slowly, very, very slowly. You cannot overcome the scoop, the guy just before you. Just you should follow the speed of the guy just before you. So it is the same situation. So you should think about which one is rate determining when you made the electrochemical cells. Sometimes you should increase the electrode surface area. Okay, so still we have the same cells here, and then again I'd like to investigate the electrochemistry on ion bar. So this electrode is of our interest. So in this situation, the ion bar electrode is called working electrode. That is to say, electrode of interest. The other electrode is called counter electrode, which is used to complete the circuit. However, actually I don't care about what happens on the counter electrodes because I'd like to investigate something on ion bar. Here is the cell symbols for the electrochemical cell. Working electrode, just straight line, and counter electrode, curved line. Why counter electrode is described by curved line? Because usually The surface area of counter electrode is larger than the surface area of working electrode because we want to make the process on working electrode as the rate determining step. So counter electrode is curved, but working electrode is just flat. Sometimes the electrochemical cell have been described by some resistance. Here, as an example, we have three different resistance. Re is electrolyte resistance. As you know, during some processes, ions are moving from one electrode to the other electrode. Moving means some rate or speed. So we could describe the rate as the resistance. High resistance electrolyte indicates slow movement of ions. It means very low ionic conductivities. The other things, Faraday resistance or resistance of charge transfer. This resistance is closely related to the reduction process or oxidation process. I have said we have some rate for the ion oxidation or proton reduction. So those kinetics is related to the Faraday resistance or Faraday charge transfer resistance. Faraday Faraday resistance or charge transfer resistance plus the other resistances. So that is the two-terminal configuration. It is time to go to three-terminal configuration. Finally, you have learned about the two-terminal configuration, working electrode and counter electrode. That's it. There are only two electrodes. In three-terminal configuration, of course, we will insert one more electrode into this electrochemical system. This electrode is called RE or reference electrodes. Reference electrodes provide a reference potential which is always constant through the experiment. So we will measure the potential difference between working electrode and reference electrode. Because the potential of reference electrode is always constant, we can easily trace the change of the potential of working electrode. Practically, this reference electrode is located nearby the working electrode to reduce some resistance between working and reference electrode. Inside reference electrode, various electrochemical reactions have been used, which is based on very well-known electrochemical reaction. For example, here are three representative reference electrode. The first one is normal hydrogen electrode, which is based on the electrochemistry between proton and hydrogen. Let me write down. So this is the normal hydrogen electrode. So which is based on the electrochemistry between H plus and H2. H plus is reduced to hydrogen gas, or hydrogen gas is oxidized into proton. So this reaction provides a very constant potential. The second thing, silver chloride reference electrode. Silver is oxidized into silver plus and then which this ion is combined with chloride and then precipitates. So that is the silver chloride. So silver is oxidized into silver chloride, or silver chloride is reduced into silver. The third representative electrode, reference electrode, is standard calomel, calomel, C-A-L-O-M-E-L, calomel electrode, which is based on a calomel reaction. Again, potential is measured between working and reference electrode. So we could estimate the change of potential of working electrode because the reference electrode provides a constant potential. However, current is measured between working and counter electrode, like in the two-terminal configuration. That is the three-terminal configuration electrochemical cell. Finally, we are on the thought experiment number 2. The title of this experiment is Corrosion of Metals in Contact. Here is some practical situations. We have a boiler here, and the main body of this boiler is made of iron, Fe. Also, a pipe is connected into the boiler, and the pipe is made of copper. Unfortunately, we have here acidic rainwater on the copper pipe and also on the iron boiler. What happens there? The answer is the serious corrosion of the iron boiler. This situation is very similar to the previous example of proton ion cells. In this previous example, ion Fe is dissolved into water as a form of Fe2+. The extra electrons generated by the oxidation reaction is going to the copper, and then finally those electrons meet the proton on the surface of copper, and then after proton gets those electrons, then finally hydrogen is evolved from electrolyte. Almost the same situation. So only different thing is copper and iron is connected by additional metal wire. But in this iron boiler situation, copper is directly contact with Fe boiler. Therefore, the same. With acidic rainwater, like proton containing electrolyte. What happens? Here is proton there, and then Fe is oxidized into Fe2+ and dissolved into water. Those electrons is moving into copper and finally reach proton, then hydrogen evolution. So we will experience a serious corrosion on the body of the iron boiler. So, how can we protect the iron boiler from corrosion? The answer is zinc plating. Let me check the reduction potential of copper, Fe, and zinc. No. Proton, Fe, and zinc. So, For this situation, we have used this one. Let me change my pointer into pen. So, oops. So, Fe donates each electron into proton, then oxidation happen, reduction happen. This is the problematic thing. This is a kind of corrosion. This Fe2 plus is converted to finally iron oxide, Fe2O3 or something like that, which is called rust. So it is corrosion process. Anyway, then right now we have a zinc. One more thing, zinc here. So the reduction potential of zinc is more negative than the reduction potential of Fe2 plus Fe pair. So zinc could donate its electron into Fe2 plus. So something like that. Let me change the color. So still proton could get the electron from Fe. So Fe2 plus is generated. However, here is a big brother. Zinc is donate its electron into Fe2 plus, then zinc 2 plus is formed. At the same time, Fe2 plus generated from the first reaction is going back to Fe. So Fe is regenerated even in the presence of H plus. I have explained this situation as the two-step, but I can say proton is reduced. Let me change the color again. Proton is reduced to H2 by getting the electron from zinc, and then zinc is going back to, not back, zinc is going to the zinc 2 plus. So we can protect the Fe. Let's go to the picture. So Fe is here, zinc is here, and of course hydrogen evolution happens like in the first example. However, the electron source is not the Fe, but the zinc. So zinc is donating its electron into Fe body, and the electron flows through the Fe body and finally reach H plus. So hydrogen evolution and zinc 2 plus dissolution into electrolyte. But we can protect our ion boiler body. This is the end of chapter 1 about the basics of electrochemistry by using two different thought experiments. Thank you.